Hello, my name is Ryan Brecky, and today we'll be discussing Pervious Concrete. Pervious Concrete is a very specialized material, but also a very sustainable option. We'll discuss some of the characteristics and considerations when using this material. We'll then talk about the applications and placement techniques when using Pervious Concrete. We'll go into the pros and the cons, and then talk about recycled materials and the use of supplementary cementitious materials in Pervious Concrete. Enjoy. The origins of Pervious Concrete come from an increased emphasis on sustainable construction. As people have become more environmentally conscious, the trend is towards low-impact developments, or LIDs. LIDs are a land planning and engineering design approach to manage stormwater runoff. LIDs use on-site natural features to protect water quality, and this approach implements engineered controls to replicate the pre-developed watersheds by keeping water that falls on the newly developed area closer to the source. The desire has also been to reduce the urban heat island. The urban heat island is the metropolitan area, the populated area, which is significantly warmer than its surrounding areas. This warmth is due to the mass of large dark surfaces such as asphalt roads and dark colored roofs, and the high density of the population inhabiting these areas. Now, for the economics of concrete, you must think that for every acre covered in impervious material, you have to import an acre-foot of water every single year. Now, this isn't a huge problem for rural and mixed-use areas, but when you get into more densely populated areas with a significant amount of impervious area, you have to import a significant amount of water. In California, 30 to 40% of electricity is used to move water north to south. As energy becomes increasingly more valuable, the natural thought is that if metropolitan areas can retain some of the natural water that falls on them, it could mean a huge energy and thus monetary savings for the state of California and consumers. The price tag for pervious concrete often scares away potential users. It has a significantly higher initial cost at almost 33% more per square foot compared to a traditional concrete. However, comparing the two is like comparing apples to oranges. The benefits of pervious can balance or even outweigh that initial cost difference. Pervious concrete mitigates the need for a traditional stormwater management system, which often results in huge cost savings. Next, we will discuss the characteristics of pervious concrete and what to consider when designing a pervious surface. At this point, you're probably wondering, what exactly is a pervious concrete? Well, it is comprised of carefully controlled amounts of water and cementitious material that create a thick paste that coats the coarse aggregates, which then fasten to each other and comprise the pervious concrete. Now, pervious concrete has little or no fines, which in our case is usually sand, and the lack of fines creates a void content of upwards of 15 to 25%. This creates an interconnected pore structure that water can percolate from the top all the way through to the bottom. Now for some characteristics of pervious concrete. Pervious concrete has flow rates flowing in one side and out the other side of 480 inches per hour per square foot, which is equal to 3 to 8 gallons per minute through that square foot. Pervious concrete has compressive strengths anywhere from 500 to 4,000 psi depending upon the materials used in the given mix, and has water contents ranging from 0.27 to zero point 0.3, which is significantly lower than traditional concrete, which would have water contents from 0.4 to 0.6. Pervious concrete has very small slumps, and oftentimes the slump isn't even measured when doing field testing because it doesn't give accurate depiction of any property corresponding to the pervious mix. Pervious concrete has very rapid set times and a faster drying shrinkage due to the fact that the voids are there, and so there's more air flow through the concrete. There are two main considerations when designing pervious concrete. These factors determine the thickness of the pervious profile. For the hydraulic factors, you must consider the expected rainfall, pavement characteristics, underlying soil properties, and the runoff that can be tolerated based on a design storm, and then determine the permeability and the volume of the voids of the pervious concrete corresponding to that. The design storm under consideration for pervious concrete is usually either the 2 or the 10-year storm, which means a storm that has either a 50% or 10% chance of occurring respectively. The subgrade soil is important to determine the infiltration rate and design of the pervious concrete. The options for soils with low infiltration rates are designing wells or channels to increase the permeability of the soil. Mechanical properties are determined based on the necessary strength and stiffness depending on the application of the pervious concrete. The American Society of Testing Materials, or ASTM, only has 2 tests for pervious concrete. The first is fairly straightforward, and that is unit weight, which is the weight of a cubic foot of pervious material. The second is a little bit more complex, and that is the infiltration rate. The infiltration rate is a field test done after the first 7 days, which establishes a baseline infiltration for the pervious material. Every year, you have to come back and recheck the permeability, and if the permeability gets below 100 inches in an hour, then you need to clean the surface. The cleaning isn't that difficult because residue isn't able to get too deep into the concrete profile. Next, I will discuss the situations and locations that are ideal for pervious concrete, as well as the specialized placement techniques for installation of this material. Pervious concrete offers advantages to the environment, public agencies, and building owners by controlling rainwater and addressing their stormwater issues. It can be used in a variety of different applications, such as parking lots, low volume pavements such as roads, alleys, and driveways, and it can be placed on slopes up to 16%. It's especially good where the cost of land is high, for example, urban areas and areas where the cost to develop is very expensive. Pervious concrete places an emphasis on sustainable construction. When deciding whether or not pervious concrete would work for your application, careful attention must be paid to the soil type surrounding. This includes the permeability and the particle size, especially with the thought of clogging and freeze-thaw resistance in mind. Freeze-thaw resistance depends on the saturation of the pervious profile. When water freezes, it expands. And if there's water trapped in the profile and it freezes, then the expansion can break apart the pervious section. Usually, the rapid draining prevents the profile from remaining saturated during the freezing process. However, if a large amount of water is expected in a frequent freeze-thaw environment, an option is to increase the base layer. Now, the increase in size of the base layer adds a larger void content and decreases the likelihood that the pervious section of the concrete will remain saturated. You could also introduce a perforated pipe to carry water away from the soil with low permeability into soil with a higher permeability. When placing pervious concrete, you have to keep in mind that it cannot be pumped. The best and most effective way to pour it is to tailgate it with a classic mix truck and let it move directly from the truck into the location where you want it. After placing pervious concrete, it has to be screeded off, either manually or vibratory. It should be screeded off about a half an inch higher than the desired top of surface. After screeding the concrete, it has to be compacted with a steel roller. Following the roller, you have to place the expansion joints. This whole compaction process has to happen within 15 minutes of placement due to the rapid set times we discussed earlier. Compaction for pervious concrete is the finishing step. Floating and troweling can close the surface voids at the top and thus not allow the water to seep into the pervious profile. The pervious section needs to be covered with a polyplastic because the water is needed for the curing chemical reaction and would otherwise evaporate because of the large void content. Curing takes about 7 to 12 days, and the concrete should remain covered for that period of time. Next, we will discuss some of the advantages and disadvantages of using pervious concrete for your project. There are a number of benefits of using pervious concrete. As I spoke of earlier, pervious concrete is an ideal material to turn any project into a low-impact development. LID is a catchphrase in sustainability, and turning a project into an LID can be a design requirement or even move a project from the design phase and into construction. Pervious concrete reduces stormwater runoff and captures the quote-unquote first flush of surface runoff. This first flush is the first time it rains after a dry period. During the dry spell, pollutants such as oil from cars builds up on the surface of the concrete. When the first rain comes, those pollutants are washed down into the soil. The soil contains microorganisms that can break down these pollutants as long as the concentrations are low. The problem with traditional concrete is that when all those small concentrations of pollutants are carried to the same place, in our case the sewer system, it becomes a higher concentration. This means that the water has to be diverted to a combined sewer system and treated the same as raw sewage, or else the stormwater would run directly into a body of water carrying all the pollutants. Pervious concrete is the EPA's new best management practice for managing stormwater. Pervious concrete offers the same ideas as a detention basin, holding the water and recharging the natural aquifer. As we talked of earlier, pervious also reduces the urban heat island. Pervious reduces the urban heat island because its open pore structure naturally stays cooler and absorbs less heat. This quality is measured by the surface reflective index. This index measures a test that shines light on the concrete and measures the reflectivity. A score of 29 certifies a surface as LEED certified. However, pervious doesn't score well on this test. The fact that it is multi-angular means that the light doesn't reflect back in the right place for measurement, so although we know it reduces the urban heat island, it is not yet LEED certified, although they are working to get it so. Pervious concrete allows for more efficient land use. It reduces the need for stormwater management devices such as swales and retention ponds. This could reduce the overall project cost on a first cost basis instead of only seeing that cost savings in the future. Using pervious concrete in parking lots can also save trees. As trees grow, their roots reach out at least as wide as their branches. As the roots expand and grow under an impervious surface, they get further and further from the water. The deprivation causes them to start reaching for the surface and into the impervious surface. This creates cracks in the pavement and adds to the maintenance cost. Pervious concrete allows the water to move directly into the soil and to the roots so that the tree never needs to reach for it. Pervious concrete also uses less resources. It can use reused aggregates, and when its 30-year lifespan is up, it can be recycled and uses the aggregates for the new pervious pavement. Pervious concrete can also increase safety by eliminating ponding and the potential for sheet flow over a surface. This is a case study of pervious versus an impervious parking lot. These pictures are taken across the street from each other at a location in Denver, Colorado. The one on the left is the traditional asphalt parking lot, and the one on the right is the pervious pavement. The bottom picture for both is the second day. As you can see, the traditional parking lot has melted significantly and has created puddles and ponding. The pervious parking lot looks significantly more dry. The pervious concrete lets the air circulate around the snow and melts it faster. As it melts, it drains immediately directly through the concrete and eliminates the puddles and ponding that you see with the impervious surface. There are some disadvantages to using pervious concrete. Comparing price per square foot, pervious has a significantly higher initial cost. Although this isn't exactly apples to apples comparison, that price increase is often viewed as a huge hindrance. Pervious is also susceptible to abrasion and raveling. This just means that because of its open structure, the aggregates in the concrete can break apart when subjected to high speeds or sharp turns. This characteristic decreases significantly after the first 2 weeks of use. The open structure also makes it more susceptible to aggressive chemicals like sulfates and acids. If these get into the concrete, they can break it apart due to their corrosive nature. The open structure can also get clogged. If it does, then it defeats the purpose. The clogging could also trap water and result in a freeze-thaw durability issue. Clogging is usually a result of clays and silt, which are smaller particles and can pass through the pores. Sand, on the other hand, typically gets caught at the top of the profile and can be cleaned easily. Now that we have discussed a few of the advantages and disadvantages of this material, we will discuss the use of recycled aggregates in pervious concrete. Recycled aggregates are made from the crushing of other concrete that would otherwise be disposed of. Some quick facts about recycled aggregates is they can be ground up and used on site or sent to a plant for further processing. The final maximum aggregate size is 3/4 of an inch to an inch. And you can have 100% recycled aggregates as coarse, but only about 10 to 20% as fines, and the remaining fines would have to be sand. This is ideal for pervious concrete because there are barely any, if any, fines to begin with. So we can use 100% recycled aggregates as coarse and not have to worry about the fines. Recycled aggregates can also be used as the base material below the pervious concrete. There are some downsides to using recycled aggregates. A huge concern is cleaning the recycled aggregates. Contaminants can prevent the aggregates from properly binding and need to be sufficiently removed. These contaminants include oil, plastic, and wood debris. When using pervious concrete, you must also remember that recycled aggregates will have a higher absorption rate and need to be pre-soaked. This isn't so much of a disadvantage as it is a concern. There have also been a number of studies on the strength of concrete with recycled aggregates versus traditional aggregates, and there have been very mixed reviews. Some say that there's a significant drop in strength, and others say there's no difference at all. The only consensus has been that the strength of the concrete with recycled aggregates is directly related to the strength of the original concrete that's being used as recycled aggregates. If there weren't any advantages, then recycled aggregates wouldn't be used. These aggregates cut costs in a variety of ways. They cut the transportation and extraction cost of mining and moving traditional aggregates. They also cut the transportation and disposal costs to get rid of old concrete. A less well-known benefit of recycling concrete is that recycled aggregates absorb carbon dioxide and thus have a smaller carbon footprint. Calcium carbonate is the material that gives concrete its strength. A simplified chemical reaction shows that the carbon dioxide reacts to yield calcium carbonate. This process happens from the outside in, and when concrete is crushed to be reused, areas that weren't previously exposed are and can react with carbon dioxide. Supplementary cementitious materials, or SCMs, are another set of recycled materials that can be used in pervious concrete. Supplementary cementitious materials are pozzolana. These are materials with little cementitious value, but that can form compounds with cementitious properties. All SCMs would otherwise go to landfill as hazardous materials. Reusing them reduces greenhouse gases from disposal and also producing new Portland cement, which has a very large carbon footprint. The three types of SCMs we will discuss are fly ash, silica fume, and slag. Fly ash is a byproduct of the combustion of coal and often comes from coal power plants. It can be used in concentrations from 15 to 25% of the cementitious material by weight. Fly ash can increase workability because it decreases the water demand. This workability means that it flows and consolidates better. It's an interesting material for pervious concrete because pervious is often very stiff and tough to work with, and the fly ash decreases the need for water and increases the workability. However, fly ash can reduce the permeability, which can be problematic for pervious concrete, seeing as the point is for high permeability. Silica fume is the second SCM that we will discuss. It is a byproduct of the ferrosilicon industry and is a very, very fine powder. Silica fume has been used in pervious concrete in extremely low amounts because it decreases permeability significantly. The maximum percentage it has been used in is as 10% and has been found to work better in quantities of about 3 to 7% of the cementitious materials. Unlike fly ash, silica fume increases the water demand. This results in the need for a high-range water reducer to allow for workability. This high-range water reducer is fairly expensive and increases the expense of the pervious concrete. The advantage of silica fume is that it develops a higher ending strength, and that strength develops at a younger age and a faster rate. This helps in pervious applications because it can decrease the cure time, which, as you learned earlier, is significantly longer for a pervious concrete at about 7 to 12 days. The final SCM we will discuss is slag. Slag is a byproduct of smelting iron ore. The iron is removed from the unwanted material, and the unwanted material is quenched in water or steam, and then ground into the slag that we use as an SCM. Slag can be used in percentages as high as 25 to 70% of the cementitious material. It slows down the rate of strength gain, but results in a higher strength at later stages. Like other SCMs, it decreases permeability of the concrete, which can be a hindrance to pervious pavements. However, slag does increase the sulfate resistance of concrete, which can help because pervious, with its high, large pore structure, is susceptible to sulfate attack. These are the three SCMs that are used in pervious concrete, and each one has benefits and problems associated with it. Thank you for joining us today for our presentation on pervious concrete. You learned a little bit about the characteristics and considerations when using this material. You learned about the applications and placement techniques, some of the advantages and disadvantages when using pervious. You also learned about using both recycled aggregates and supplementary cementitious materials in pervious concrete. Pervious concrete is a very unique material. It's not for every job, but when used in the proper applications, it can be a very effective and sustainable alternative. Thank you.